Hello everybody, my name is Benjamin Dane. I'm a senior student here at Embry-Riddle Aeronautical University, and this is our senior design project, a real-life portal turret. For the next couple of minutes I'd like to show you all of the features of the portal turret and what went into the design of such a device. The Portal Turret project began as a collaborative effort between a five-man team made up of myself, Benjamin Dane, along with Josh Chang, Jet Nazareno, Randall Smith, and Carlos Gaxiola. Now, before we had started this project, we had done a lot of research and discovered that other college teams had attempted a similar project, but in all of those cases they designed what we called a tethered unit, meaning that the portal turret had to be connected to some laptop computer which provided it not only with a power source, but also with the processing power necessary to allow the turret to see. We had a very short design timeline for this project of about one academic semester or 4 months, which meant that we had a very short amount of time to not only figure out how we're going to make this project work, but also to source the parts, design our printed circuit board, and build the thing. To that end, we decided to use the mbed microcontroller as it provides superior processing power and also has a large suite of I/O capabilities which we would use to interface with the various peripherals we would need for this project. For the circuit board for the portal turret project, we decided to go with a through-hole setup, not only because it's a lot easier to solder in the components by hand, but also because it's a lot simpler for us to design. As is the case with most PCB-driven projects, we had 2 design iterations, the first of which was just to get everything on the board and make sure that it functioned, and the second of which was to iron out all the problems we had with the first iteration. For our software, we had several distinct modes which defined how the portal turret operated, the first of which was a power-on self-test diagnostic cycle, which ensured that the turret was operating properly once we started it up. The other 3 defined the operation of the turret before and after it had received a target, which were standby, searching, and engagement mode. We coded the project in C++ because it was the primary programming language for the mbed microcontroller, and we used the mbed's online compiler as our development environment. The design of the portal turret was an iterative process, meaning that we went through several distinct phases before settling on a finalized product. The first phase, affectionately known as Hobo Turret because it existed inside a cardboard box, was composed of 2 breadboards to which we had mounted the main electrical components. We used this phase to see how the components would interact prior to the design of our first printed circuit board. The second phase, known as Lego Turret, because it was composed of the first printed circuit board and a Lego chassis, was used to determine the mechanical properties of the turret. Combining these first 2 phases together, we designed the APeRL version of the turret, which was meant to emulate the look and feel of an actual portal turret as much as possible. It's primarily composed of aluminum rods, MDF board, and plastic project boxes where we mounted the electronic components. Using a custom-built vacuum former, we constructed a polystyrene shell that resembled the outward appearance of a portal turret. Originally, the portal turret was designed to fire 2 BB guns as its primary weapons. Unfortunately, due to a design oversight and a lack of time to correct it, we were unable to add this feature in the final version. However, it would be very easy to incorporate this feature in further revisions. After powering on, APeRL needs to run through a self-test diagnostic sequence, wherein she tests her camera, sound output, turret orientation, and wing position. This is to ensure that in case of some anomaly during the power down sequence, she starts off in the perfect position to enter standby mode. APeRL reacts to green targets, as seen here. Once a target passes in front of APeRL's vision, she automatically extends her wings and begins tracking the position of the target. She moves her turrets to aim towards the target, as seen by the laser pointer, and once she has seen the target in the same place for 3 consecutive frames, she fires on the target, in this case as heard from this beeping sound. When the target is removed from APeRL's point of view, she centers the turrets again and waits for a full minute before returning to standby mode. During this time, she's outputting various sound clips to indicate that she is still looking for a target. Eventually, APeRL re-enters standby mode and closes her wings.